Hi, in this video I will talk about numerical solutions for ordinary differential equations of order n. In the previous video we talked about numerical solutions for the first order ODEs. Here we are talking about ordinary differential equations in this form, where we have the derivative of order n of y with respect to x, and on the right hand side we have a f function, which is the function of the x and y and the derivatives of y with respect to x until order n minus 1. So the x is between the interval of a and b, and to solve the problem, basically we need to consider initial conditions, as we discussed before for the first order ODEs. Here, in addition to the value of y at the initial point a, we have to also consider some initial conditions for the derivatives, the first derivative, second derivatives, up to the derivative of order n minus 1. So these are the essential conditions, which we call it initial conditions. If we impose these conditions on both ends, on a and b, then we call these as boundary conditions. And also the form of this problem, we call it boundary value problem. The first step is to reduce the nth order ODE to a first order system. So the motivation here is to use numerical techniques that we have already introduced for the first order ODEs to solve a nth order ODE. So for this purpose, basically we have to write the ODE, the nth order ODE, as a first order system like this. So basically this is again the same as the first order ODE. The difference here is that we have the bold y and bold f here. So the bold y basically here is the vector of the derivative. So the idea is to treat the first n minus 1 derivatives of function y explicitly as unknowns. So we assume that the n minus derivatives are unknowns and construct a vector of y. So basically this vector of y, the components, is the derivatives of y up to order n minus 1. So the I component basically is the I minus 1 derivative of y with respect to x, where I changes from 1 until n. So basically the last component is the n minus 1 derivative of y with respect to x. Using this definition, we can write the components of y. So basically these are the components of the y bold that I introduced in the previous slide. So the first component, y1, is y, and the second component is the derivative of y with respect to x. So from the previous definition, we know that y is y1. So basically this y1 from the previous component, we can put it here, and it becomes the derivative of y1 with respect to x. Okay. So for the third component is the second derivative of y with respect to x. Again, we can use the previous component y2, and since y2 is the first derivative, is basically the derivative of the first derivative becomes second derivative. So basically here we can write the second derivative as the first derivative of the previous component, which is y2. Okay, so this is basically first order. This is also first order, no? This the first order derivative of y with respect to x. Okay, so you see that all the components can be written as the first order derivatives by using the previous components. So basically you see that the second order derivative becomes first order derivative by using the previous component. So for the last component, yn, basically this is the n minus order derivative of y with respect to x. Again, this n minus order derivative can be reduced to the first order derivative by using the previous component. Okay, because the previous component is basically n minus 2 derivative, so the derivative of the n minus 2 derivative becomes n minus 1 derivative. So this is basically first order again. So you see that all the components of the y, the bold y, basically can be written as the first order derivatives using the previous components. Using the previous definition, then we can convert our nth order ODE, so nth order, to a first order. So this is the first order. This is first order ODE. So you see that instead of using high order derivative, for example, the n order derivative of y with respect to x converts to the first order derivative of yn with respect to x. The other component is the same. The first order derivative is y2. The second order derivative is y3. And the last components, the n minus 1 order derivative is yn. So all of the high order derivatives convert to the first order derivatives, and finally we come up with the first order system. As a result of this conversion, basically we have a system of n first order ODEs. So each one of these ODEs is first order, and we can use the techniques that we introduced for the first order ODEs to solve each one of these ODEs. Okay, so basically this system we can call it basically the first order system with n ODEs. We can write our first order system in vector notation. So basically the first order ODE can be written in this form, where y, basically the vector of y is defined here. So different components of y as I introduced in the previous slides. And then the initial condition also can be written in a vector form. So basically the different values of y components at a can be prescribed by the vector of alpha. So the alpha is defined here, alpha 0, 1 until n minus 1. And f, basically the right hand side term, basically again is a vector of different components from y2, y3 until the f, which is the value of f at different given values of x, y1 until yn. An example of application of higher order ODEs is to find large displacements in a cantilever beam. So the cantilever beam is represented graphically here. The beam is fixed at one end, and we apply a point force P at the other end. We also apply a distributed load of W along the beam. The beam has a length of L with material properties of the Young modulus E and the second moment of inertia I. As a result of this condition and also the load that we apply, basically the beam shows this large displacement, and the displacement is represented by this psi, which is the slope or the angle of the deformation, and this s basically is the distance along the beam. So as we will see in the next slide, this deformation can be explained by a second order ODE. The second order PD is written in this form. Basically, this is the second derivative of psi, the slope with respect to s, the distance along the beam. The S is in the interval between 0 and the length of the beam here. And basically the other terms is based on the load that we apply and the cosine of psi. So we can impose two different conditions for this ODE. The first one is the boundary conditions, where we impose some conditions on the first point and the last point of the beam, and the other set of conditions we call it initial conditions. Okay, and the initial conditions, basically we impose some conditions only on the first point, 0, the derivative and the value of the slope. So notice that in both conditions, basically we have to impose two conditions, one for the derivative and one for the value of the psi. So if we want to find also the deformation of the beam, basically we can solve two additional first order ODE. The first one is for x and the second one is for y. So basically the definition of this derivative, the first derivative of x with respect to s, is based on cosine and sine. And of course, again, we have to impose some initial conditions for these two first order ODEs, as you can see here. As before, we can reduce our second order ODE to a system of first order ODEs. So basically the first order system can be written in this form. This is again same as before. We discussed this before. So we have to define a vector of y, the bold y, and also the f with some initial conditions of alpha. Okay, so the vector of y is defined as two components, y1 and y2. The y1 is the side, the slope of deformation, and the y2 is the derivative of psi with respect to s. So the corresponding terms for f basically is y2, and then the terms that depend on the material properties and also the force that we apply. So the alpha, basically the initial conditions, is defined as beta and 0, as we discussed in the previous slide. This is again a vector of two components. If we want to include geometry description in our system, basically we need to add the two first order ODEs that I discussed for x and y into our system, and add two additional components of y3 and y4. Okay, so the corresponding terms in the f basically is the cosine and sine. Again, I discussed this in the previous slides. And we also need to include two additional initial conditions, which both of them are 0 for x and y. So the additional, basically the additional components would be the components of x and y, which describes the geometry or the deformation of the beam. Here is the solution of our first order ODE system for the cantilever beam. Here we consider Euler method for solving our first order system with M20 and beta 1.13. So basically here in this graph, the blue graph is psi, or the slope, and then the green one is the derivative of psi with respect to s. So you see here that at the initial point, basically psi 0 is beta, which is 1.113. So you see that we satisfy the boundary condition. Here also we have another initial condition for the derivative at point 0, which is 0. Okay, so basically this beta and 0 are the initial conditions. that you can see that we satisfy from the solution. So here in this graph we see the deformation by solving additional first order ODEs for y and x, and basically it shows the deformation of the beam. Here we compare the solution using both Euler and Runge-Kutta order 4 method. We expect that at the end of the beam the slope becomes 0. If I plot the beam again here, the deformed beam, basically the beam is fixed at one end, and at this point where the beam is fixed, basically the slope should tend to 0. So you see that with the Runge-Kutta order 4 method, with the number of subintervals 10, basically we get the better solution with respect to the Euler method. So in the Euler method, when we increase the number of subintervals from 20 to 40, basically the result tends to 0, the slope of 0. In the case of the deformation, is the same. The Runge-Kutta method gives us the more realistic solution, where at the end, basically the slope tends to 0 here at the end of the beam. And the solution of all these methods, basically at the beginning of the beam, when we apply the force, are more or less similar, but at the end diverge. Here also we analyze the convergence of both Euler and Runge-Kutta 4 method for the cantilever beam. Here for the solution, for the reference solution, we consider the slope at the end of the beam is 0, and then we calculate the error with respect to this value. If you see in this graph, it is obvious that the order of the Euler is 1, so the slope of this line is 1, and for the Runge-Kutta 4 order 4 method is 4, so the slope here for the Runge-Kutta is 4.